Right, thanks everyone for joining us on this live CPD event today, where we're going to talk about a bit more about shear studs and specifically construction details that involve shear studs and kind of the impacts of those dimensions, etc. So today I'm going to talk about shear stud configurations, a bit about the design rules. We did have a shear stud CPD some months ago, maybe even into last year, where we talked about what a shear stud was for, but we will touch upon that and then we'll go into the design rule bits. But it's going to be more about the details with our products, so that's the SMD floor deck products, and then some practical considerations around studs, where you need to think about them if you're specifying shear studs or designing beams with shear studs. So if we start with the design rules, and we're going to take a look back really at what we did last year. What is a shear stud for? So a shear stud is, in the sense of we're discussing it today, a shear stud would be welded through the deck to the top flange of a beam, and once the concrete is poured and hardened, that then forms a composite beam with the steel beam and the concrete acting as one, with the transfer of force between the beam and the concrete facilitated by that shear stud. So those shear studs have certain shear resistances within the concrete, and they need to transmit a certain amount of force between the concrete and the beam and vice versa, in accordance with the composite beam design. So you will have an effective breadth of concrete, which is effectively giving you a larger flange to the top of that beam. So that's very brief. We went into it more last time. That's very brief what a shear stud is doing. It's linking the two together, making the beam and the slab all one composite element. And I talked about the resistance of the stud. More often than not, that resistance is caused by, or the ultimate resistance of that stud is governed by a failure in the concrete. So you get a cone of failure over the shear stud. And that's obviously subject to the height of the shear stud, the grade of the concrete, the position that it's welded within the composite deck profile. And I'm going to talk a bit about those kind of things today. So you can see there an image on the right. That is a stud that has failed, and then we've broken away the slab, and you can see that the slab has ductile. It's a loud slip within the slab, but it's also then you can see the cutaway cone of failure. It is actually possible as well for the stud to fail, not just in the concrete. It could fail at the weld, but pretty much the governing factor is nearly always the concrete. So that's a very brief look that was at what a stud is for, how it fails, and that's all we're going to really cover in terms of the kind of crude stuff on it today. It's going to be more about the dimensions, the minimum distances and configuration aspects for studs. So if I'm designing a building with shear studs, what are the key dimensions and impacts that can have on my design? So there's a number of minimum dimensions that apply. You can see them on the screen here. They typically all relate to the diameter of the stud, and in UK and most of the world, 19mm diameter studs are common within composite floor slabs. So for composite beams, we'll through deck a 19mm diameter stud through the profile onto the beam, as I mentioned earlier. And the minimum dimensions that we see over here, 30mm minimum, are a requirement of the design standard with regards to the end of the sheet, and then a requirement to the toe of the beam. And you also have spacings within those studs. So the minimum spacing is there because those rules for resistance are based on something. So as studs get closer together, the resistance of each stud reduces because the cone of failure effectively overlaps. And then the maximum spacing, you're trying to minimize uplift between the stud positions. So there is a maximum spacing allowable as well. Similarly, if you have pairs of studs, so you need more shear studs than one would be permitted per trough. Then you also have minimum dimensions for a similar reason. As these studs move closer together, they become more like acting as one. So you need to maximize the distance between the pair to maximize the resistance of each stud within the group. And the minimum requirement for that is 4D. And similarly with staggered, there's rules for staggered studs, where you may be staggering studs, which is common at butt joints in the deck profile. There's also a number of other minimum dimensions around the stud within the sheet. So the rules, the bits I spoke about earlier, were very much along the beam line or across the beam flange. There's also distances, minimum requirements within the profile itself, and that's obviously to provide an effective concrete area around that shear stud to give you the resistance for the shear stud within that profile. And the resistances are calculated in accordance with the relevant design standards. So we're talking whether that's BS 5950 in old money or Eurocode 4 as it is today. Then the rules are based on these minimum dimensions and positions. Many profiles do not permit these studs to be out of position anyway, SMD's profiles being one. We have these stiffeners that naturally mean the stud is positioned centrally in the trough, and this is a re-entrant profile, but our R51 plus profile has similarly stiffeners in the bottom pan, which means the stud is positioned centrally, which means the minimum dimensions are typically achieved. One thing to note as well is the height of the stud, and the height of the stud needs to clear the profile. And I've just noticed a typo there. That should be 35 millimeters or 2D, not 3D. That should be 2D. That's an error on the slide. Can you make a note of that, Pete, so we can change that? So that should be 2D, which is actually 38 millimeters, but commonly a 100 millimeter stud, which is 105 millimeters before weld, 100 millimeters after weld if you weld directly to steel, but is under 100 millimeters when you weld through deck, is used on a 51 or 60 deep profile, and our 80 deep profile will have a longer stud, so it will have a 120 after weld, but 130 pre-weld. So it is important to realise that there's a minimum stud length within any profile as well. It's also important to make sure you type it right, which we didn't there. It's 2D though. So using those rules, all these limits from the code, that then gives you design resistances. But what it actually does is give you a K factor, as it's known, or and that factor reduces the stud resistance within a solid slab. So in the design process, you calculate the stud in a solid slab, the resistance for a stud in a solid slab, and then you reduce that stud resistance based on a number of profile characteristics. And there's equations to do that. They're all in Eurocode 4 and similarly in other design standards. And it's all about the profile depth, the trough width of the product, the stud height, so how high it is above the profile, and then the number within that trough. On the left here, you can see the rules for SMD profiles, and you can see that for certain scenarios, you can actually achieve the same stud resistance as you would in a solid slab. That's typically where the beam is parallel, so in these kind of situations. But you can see where it's trapezoidal and the beam is perpendicular to the deck span. So in this kind of scenario, and the fact that you have these gaps here does reduce the effectiveness of that stud compared to a solid slab. So you end with reduction factors on those shear studs, as you can see over here. They can all be calculated in the code. We've just done them in a table, and that is available on our TGN online website, which I'll talk more about later. So it's very much about the shear stud, the resistance, the strength of that stud. We're now going to talk about what spacings can and can't be achieved. So it's only worthwhile designing a beam compositely if you can get the studs on that beam practically. And this is really where this comes in. So the profile influence is an important one, particularly for beams that are perpendicular to the deck span. So we have a number of shallow floor deck products. the R51 Plus that you've heard me mention already, that is 150 spacings, so 150 trough spacings, so permits a stud at 150 centres across the profile, or pairs, you know, at multiples of 150, but nothing different. And the trapezoidal profiles we offer are TR60 Plus and TR80 Plus, and they permit a 300 or 333 centre. The TR60 Plus has 333 millimetre trough centres. The TR80 Plus is 300. So the orientation of that profile, when it's at right angles to the beam centre line, is key to the spacings that can be achieved. Many steel beam design softwares out there obviously have our products in and are aware of those spacings. But the key thing is when those beams aren't perpendicular to the deck span. And we're going to talk a bit more about that in a moment. There's also changes in span direction. So we're talking very much about the span at the moment. Changes in span direction can impact on the stud centers that you can achieve. So obviously in this scenario, on the left-hand side of this beam, you would be governed by the trough centers, but on the right-hand side, you could actually achieve closer spacing. So perhaps on that beam, by looking at it in specific scenario, you could actually design it with closer than 333 centers, depending on how big the beam center is, the beam width is, sorry, and where you can put those studs on that right-hand side. There's also then implications of how you get those studs on to the beams with that voided area where the beams are parallel. So this would be a situation where the beam is parallel to the deck span, and the deck has been set out on that beam. So this is there's no need for a flashing, but you can get the studs onto that beam welded through the flat at the edge of the profile. That isn't always the case. That's obviously fine at a set out point, but if the primary beams, so those parallel beam centers, do not coincide with the centers of the troughs of the product, so the TR60 as we see in this image, then that impacts on whether you can get studs on that next beam along. And in that scenario, you may end up with a rib over the beam that looks something like that. And then we would have to achieve that, you would have to cut the profile back, add in a flashing detail, something like that blue one you see there. And that then enables you to get those stud centers or the shear studs onto the beam. And because it's a parallel beam, at the centers required within those minimum and maximum spacings. Flashings are slightly different with an R51 profile, but the principle's the same. The one thing I would say about R51 Plus or the reentrant profile is that it's very flexible for stud position. Because there's that much more flat of the profile, it's easier to then get studs onto that beam. A couple of things, so just to note about trough spacings. Excuse me for a moment while I have a sip of my coffee before it gets cold. Is one thing here, this is a TR60 Plus at the top. You've heard me mention it. Ours is 333 trough centers. So you can see there 333 from rib to rib, 333 from trough to trough, however you look at it. Other products in the marketplace do differ. So comparable products, and when I say comparable, other people's 60 mil trapezoidal profile will have different trough spacings. So the key thing to consider is if you're designing a 60 mil profile, it's best to start with the wider center, and then anything else will suffice as well. What we find sometimes is that people start with a 300, then they want to change a product, maybe whether it be ours or another who doesn't have a 300 trough spacing, and you end up with potential situations where there's problems with stud centers and getting the number of studs on, etc. Because the key thing is the wider the trough spacing, the less material in the product. So in terms of use of raw material, wastage, etc., then the 333 spacing gives you less material for, in many cases, the same design. So it's just important. It would be a recommendation to use a 333 center of stud across troughs initially, and then you have the flexibility of change without too much difficulty in terms of a specification. So, but it's just key to realize that not all 60mm trapezoidal profiles in the marketplace give the same trough centers in terms of shear studs. I think that's just the important note there. I've looked at that and what that means in terms of compared to a 300 trough. So just on this relatively simple example here, you can see it means less studs on the beam naturally because they're slightly further apart. The factor for each stud is pretty much the same, although slightly different because of the geometry of the profiles, as we talked about earlier. And the longitudinal shear resistance is then reduced because of that one less stud. But as I said earlier, it may well be that beam only requires this requirement. And by considering that, you're utilising less concrete, less raw material in the steel product itself. And that ultimately leads to some savings along the way, and also gives you flexibility should you need to change spec at the end. But it is just an important thing to realise for those who don't deal with decking every day like ourselves. So if you need more shear connection resistance with 333 centres and you can't get it, there are a number of ways of doing that, whether it's pairing up studs, whether it's having a kind of non-standard stud specification. They're not ideal and you don't really need to do it that often. So this would be your single studs. If you can't get your required shear connection, you can always pair them, but that's obviously double the amount of studs, so not great from a use of material, etc. You can then add extra studs at the ends of the beams where the shear is at its worst, and that ultimately means you can get up to a number to get your resistance, but you don't need pairs along the whole beam, or you could, if you want uniform distribution, alternate between. There's many different options. There are composite beam checking tools online. There's also this guide, which I would certainly point you to, which is the SCI guide, which has, I would call, advanced rules over the current Eurocode 4 rules for shear studs, and particularly partial utilisation and shear connection rules. So certainly a document to pay attention to in relation to the subject we're talking about here, which is very much about achieving the adequate connection between your beam and the concrete that we referred to at the very start. So the adequate force to transfer. Bit more on profile influence, or a slightly better image really, is when you start to look at single stud to double stud to maybe more than 2 studs, you start to need wider beams. So I mentioned the 30mm from stud to the edge of the beam at the very start. And obviously, as you pair up studs, you have a minimum distance between those studs, and you have those minimum distance between the stud and the edge of the beam. And what that ultimately means, as the more studs there are in a trough, the wider the beam needed. And all the dimensions for these different beam widths are within our TGN guidance in 2D format. But this is just an image to kind of show how the beam size needs to widen as we get more studs. So I've talked very much about studs being perpendicular or parallel. Sorry, beams being perpendicular or parallel to the deck so far. And that's not always the case. And this is really where, in relation to shear studs and standard details, we probably come across the most issues, or the most challenge to get the right number of studs on. So this on the right here is the perfect scenario of 90. The beam is at 90 degrees to the deck, so you've got a stud at 333 centres, depending on the profile. Looking a bit further into that, when you have a raking beam, so this is the perpendicular beam, 333 centres, trough centres, as we say, perfect, no problem. We can get them on at 333. A lot of beam design software naturally puts studs at 333 centres, or 1 per trough. Now, it would even potentially do that on this raking beam, depending on the package you're using. But on this raking beam, studs at 333, for obvious reasons of where the troughs line, which you can see by these chain dotted lines, would not be achievable. And this is a good image to show that. The studs are at 333. All the red ones in this image clash with the profile. So if you look in this 3D image, you can see that they're clashing with the ribs in most areas, and you wouldn't physically be able to weld them. So what that means is if this beam is designed with studs at 333 centres, they actually can't be welded at those centres. What can be done is studs in this particular scenario with the angle of beam we have here is studs at 521, because that's the way the ribs fall when the deck is not running at 90 degrees to the beam for this given angle. So it's important to realise that if we design a beam with 333 centre studs and the deck is running at not 90 degrees, that the studs may not be possible to put in at 333. So in this scenario, it's 521. You can obviously pair those studs up, but then do those pairs give enough resistance across the beam? So there's a load of questions around that when looking at raking beams across a deck span. There are some exceptions to this. So one would be if that beam is wide enough, there is potential to achieve 333 centres, because you could stop and start the profile on the edges of the beam. So providing we've got a 50mm bearing for the deck on both sides, you could then have a gap down the middle of the beam between the decks to get the studs on. I wouldn't necessarily recommend that for two reasons. One, it's a lot of rake cutting on site, so a lot of work at height, a lot of wastage when you're cutting those because sheets are square cut ends. And secondly, it's not the best detail in terms of the studs would then be positioned against a rib, and you would need a wider flange to achieve that. So you may need a wider flange, bigger beam, which in actual fact would have been better designed non-composite because of its scenario. So design a non-composite beam and it works. Alternatively, if you had an R51 profile, you would have a lot more ability to get the required number of studs on, because we said the troughs are at 150 centres, so the shear connection can be higher because of the number of studs you can get on the beam, and there's a lot more flat on that beam. So kind of the summary comment would be, if you have a job with lots of raking beams, and I've seen, you know, jobs that are circles that look like a bike wheel almost, then it's definitely recommended to use a product with more flat in the profile if you're designing your beams as composite. If the beams aren't designed composite, then shear studs are obviously they're not so critical. You may be using them for robustness or other purposes, but they're not, the spacings won't be as critical as they are when the beams are composite. All these things you can see on the bottom left, I didn't point out at the start, but a lot of tags come up. That is a tag to our TGN online, and this information that I'm presenting is available there. So we've talked so far very much about studding on site. So what can we do? What can't we achieve? There are situations where the studs may be put on the beam prior to attending site. So they'll be put on in the fabrication shop, the steelwork contractor's factory, and they will be welded into position such that when the decking is supplied and the deck contractor comes along to fix, they're fixing around that. This is just a number of key things required in relation to that. So we work on jobs where this happens relatively often. So you may have aggressive environments. They want to paint the entire top flange of the beam. So they want to paint, they want to weld first, then paint the entire beam to protect against corrosion. So for durability purposes, when you're doing that, then there are a number of rules. So firstly, the studs need to be positioned to align with those troughs of deck, particularly if the beam is narrow, like we see here. So in that scenario, we would liaise with the steel contractor early and advise them where the deck will be set out, where the troughs will then fall, so then where the studs on each beam should be positioned longitudinally along the beam. You then have a requirement for the stud to be on the centre of the beam, and we recommend a 40mm strip there so that there is a tolerance either side of that stud, both in the sheet length of the profile and the stud position. What that ultimately means is the minimum beam size should be 140. If I'm honest, I would recommend it be 150 and above to give you a bit of more tolerance in here, but the actual minimum would be 140 because you need a 50mm deck bearing on both sides and then some tolerance in that stud position. What we find in practice is due to erection tolerances that it is sometimes 140 isn't enough. So if you looked at a 152 or something like that top flange, then that's just giving you that little bit of extra tolerance to get those sheets in without any adverse impact on the installation. Obviously, if you've got pairs of studs, the rule changes. It just widens the minimum beam requirement for the same reasons that we kind of were saying the beam widens for a standard scenario of pairs. This just shows how the stud should line through the trough. With R51, it's I say less critical. There's obviously a little bit more range within this period, within this area. If that was a trapezoidal profile, then it's even more critical because you could have it right up against a rib of the profile, which would then impact potentially on the resistance of that shear stud. So that's it really in terms of shear studs on their own and their spacings and the beam and how that impacts. VoidSafe, I don't know if anyone in the audience is aware, but that's a void solution that we offer. And there are a number of challenges with that, and they can impact on the stud positioning as well. So this is a VoidSafe edge trim. I don't know if I've got a, yeah, it's coming, there's a better detail coming, but this is a VoidSafe edge trim. And a VoidSafe edge trim is essentially a recess trim, because what that allows is over that void, we then can apply a GRP grating to protect that void, both during construction and the life of the building. As you can see there, the trim has a minimum bottom leg. That's to enable us to get a fixing in. So the fact that this trim has this recess then impacts on where the stud can be positioned on the beam. You see here, if you have a relatively small beam and the trim, the slab edge is positioned on the edge of the beam, then we have instances where it's very difficult for everything to fit in. And clearly in this scenario, you would not be able to get a stud into this edge. So there are minimum dimensions that then apply. The minimum dimension from it's all about the inside toe of the beam to the outside of the slab, because that then gives you the ability to get your stud into position and also get your slab edge trim on, fix it in place, and ultimately following that would be the GRP system that would be on top of that. It's just being mindful that when we're looking to use a void protection system such as VoidSafe and integrating that within the slab edge trim, which has a lot of benefits, you don't need handrail around voids, etc. Then there are then impacts on the studs on that edge beam and what can and can't be achieved. As I say, all of this is on TGN online, so the reference is there when you need it. Just a bit more on that subject. So the single stud we saw earlier, similarly with double stud, that dimension gets bigger because you're suddenly needing a bigger beam. And if you have an area on a beam between two voids there and you want to tie that concrete to that beam via the use of shear studs, as you may well do, then the impact on slab edges. So you couldn't have slab edges on the edge of beam on both sides, void safe, because this would all clash with each other and you wouldn't then be able to get a stud on. So it's like a finger beam between two voids. Yeah, that's really covers that, I believe. And that's it in terms of sort of the slab edge stuff, because the slab edge stuff is largely standard and in the code. It's only when we're using VoidSafe that you have to start looking at slightly different rules for shear stud positioning. They're not typically a problem, but it's just important to be aware of them. Some other practical considerations when using shear studs. So this is one that we come across from time to time. So a step in a building, the bottom beam is composite in this situation, but there is a minimum clearance distance for us to be able to actually weld those studs. The gun itself and the size of the stud is the governing factor there. So the gun you can see here plus the stud is 550. Obviously, if we have a longer stud, that dimension increases. The scenario there would be that if this clearance wasn't available, we wouldn't actually be able to put studs on to that beam. There are ways of putting studs on, not through the standard through deck welding method. It would have to be done by another or in that scenario, the best solution would be to either pre-weld those studs because we don't have the clearance, so do it in the fabrication shop and it just impacts on the set out of the deck slightly. Or the other option would be just design the lower beam non-composite, might mean a slightly heavier section, depending on the span of your beam, a heavier section, but avoids this need where we've got a beam that we can't weld the studs to, and then we're having to get sort of site welding expertise that's not the standard through deck weld shear stud method. Bit as well, so we're talking about details on site now, about crane voids. So it's not uncommon to have to weld half of a beam and then the other half following the infill of a crane void. So tower cranes and hoists, we're talking sort of high-rise stuff. In those scenarios, we would typically be putting some form of a trim maybe on the edge just to create kind of a toe board onto that last section of deck. The concrete would be poured, leaving a construction joint back from that beam, and then once that crane is taken away, we would then perhaps come in, install the deck and weld that second half. Another option in that scenario, purely because that might mean a very small amount of welding of shear studs on a visit to site, which can be costly because you have to mobilize the rig and everything, stud welding rig. The other option there would be to use a different type of shear connector on those beams, or not design those beams local to the crane as composite. Just a couple of options really. You could use an HVB that's by Hilti or something similar. You're probably going to need more of them, but the same gang that install the deck, the nets, could install the HVBs as well. So you're reducing the cost of that return visit, because that's typically what crane voids are. They're a return visit late in the day. As the crane's removed, we then go back in and fill those voids. A couple of things relating to shear studs, so not so much about the rules, is broken ferrules. We regularly get asked, can ferrule or do ferrules have to be removed prior to concrete pour? Or can broken ferrules be absorbed in the concrete pour, as the question says here? And the answer to that is yes, they can. There are a number of considerations, and it's one for the project structural engineer to be comfortable with and approve. But ferrules, as we can see on there, they have a high compressive strength once they've been, they create an inert material. The high temperature of the weld results in that inert material with a high strength, and the density themselves, they're typical to normal weight concrete. So they're not adding weight to the slab. They have the same or better compressive strength than most concrete. There is Nelson literature and testing being done on that that we have available. So it really is, and most of the time, ferrules they have to be broken away from the weld, because you have to inspect the weld to make sure that weld is acceptable. You inspect the weld, you then ring test, you then bend test. So once they're broken away, providing they can be dispersed and they don't sort of group in one big area, then there is the Nelson information indicates there's no reason that they cannot be left on the deck, and then ultimately an additional aggregate within the concrete pour. So you can see here they've been broken away from the weld and there's bits dispersed around, not conglomerated together. I mentioned a couple of slides ago, HVBs, they are a shear stud alternative. They have a number of benefits, but then they have a number of less attractive properties as well. So the benefit is no hot works. They can be installed by the same guys that are installing the decking with the same tools, without the need for a welding rig, generator, certain power requirements that are required for shear stud welding. However, they are more expensive and they can be slower to install. So there's certain scenarios where they're suitable. Like if you're limited on hot works, they can be installed on painted beams, which welded shear studs can't. So there is a number of key areas where you'd think, okay, this is a benefit. The biggest thing is that they do not provide the same shear resistance as a welded stud. So if you're going to design a beam compositely and your intention is to use them, then they should be used from the designed from the outset. Or if you're looking perhaps you've got a job, it's not many beams, they've had the top flanges painted, and you're trying to justify that design, and you're thinking, okay, I can't weld studs, or I can't get an earth cable to it. Then you could look at this as an option, but you would need to look at the resistance of the HVBs and compare that to the welded shear stud. The resistance of an HVB, typically, a rule of thumb is about 2 for 1 you'd need. It's not always that, it does depend on the requirements of that specific beam, but they are more expensive and they are less resistant. So that really limits where they're used. But small quantities, small jobs, there is no reason why they're not an attractive proposition, because you don't then have the requirement of getting the welding rig to site, etc. So there's kind of a minimum quant that a welding rig needs, and there's a quant that where this becomes actually a attractive proposition. So it's there. There's design guidance and a Hilti software online available for those now. That's all in our TGN as well, as you can see in the bottom left. So the information is there should you need it. With that, go on to just a couple of references that are useful. I've mentioned TGN online a number of times, so hopefully those of you listening may already be aware, because you will have obviously seen our invite, seen our website. TGN online is effectively where most of the imagery you've seen today resides, and that is there shared for designers, customers, specifiers to use. It's a Wikipedia site, so it's easily searchable. We also do publish hard copies, but in this day and age, we tend not to send so many out, trying to do our bit for the environment, etc. So we share in it online, and obviously online is always more up to date than any hard copy anyway. So that's there, that's a tool available. You can also, our design software is available, so that's SMD Elements design software. You can design floor and roof deck profiles. There is a selection relating to shear studs in there, but we don't design it's not a composite beam design software, but there are benefits of having shear studs on a beam in the composite slab design. So that's the only link to really today's subject. But the profile is there for designers and specifiers. Sorry, the software is there for designers and specifiers. We have the white book. These are just a few of our tools available. The white book is the kind of old school load span tables lookup book. It also has some graphs in there that enable you to focus on an area of that guide rather than having to thumb through the multiple page document. So hopefully that's of use as well. And I think the last one, although there may be one more slide, we have the Element Span Check app. So this is very much based on the white book, but a quick tool for that, where you select your loadings, your fire rate and your mesh, etc., and it will give you your maximum unprop spans. It was kind of born out of the idea of people on site having a way of checking if they had to cut a sheet down, or if they were wanting to rotate a span, would that profile work for the required criteria. So it's there, it's available on Android and Apple. It also has functionality to get some of the downloads that are available on the website. You can also look up the checks you've done in the past, so you can save checks, and there's a way of asking a question, and there's some frequently asked questions. So you can see one there that was related to standard fixings, but there's a number of those, the more common ones that come through on our technical help desk, and there is also a way of asking a question, and that will come into our technical email, and the technical help desk guys will then be able to help. And there is one more. There's the YouTube channel, which has a lot of videos. I say a lot, we're gradually building that up. You will have heard me speak for long enough today, but there are some videos with me speaking again, largely around the software, tutorials on elements for both floor and roof. There's also, we have a series now of with this more interesting looking chap than me, and it's really on certain subjects around the stuff that SMD do. So we have one about site prep for an installation on site. We've got one on a straight edge survey, so how to do a straight edge survey on a composite slab that's been poured on. So it's on a deck that's been concrete that's been poured on decking and how you assess the surface regularity of that slab. And the recently launched one, which was about a month or so ago, is all around deflections, acceptable deflections, how deflections need to be considered, and if you want a flat slab at an upper floor level on a deck, what you need to kind of think about to achieve that, because it can be achieved, but there's a lot that needs to be considered, and it needs to be considered very early. Yeah, all those videos are available on our YouTube channel. And that's me done. Any questions? I haven't seen any pop up. Have you? I don't know if you have, Pete, anything?
No questions.
If anyone wants to ask away, then by all means do. I will stay on for 2 or 3 minutes. So if you'd rather ask when there's less people in the room, I'm sure people will begin to leave. But otherwise, yeah, thanks for listening today, and look out for our next one, which will probably be next month or maybe towards the latter part of next month. I don't know the subject yet. I don't think we've firmed that up, but we do these typically every month. So keep an eye out, and hopefully there'll be other subjects coming soon that you'll be interested in. Thanks very much, everyone. Goodbye.